What if I told you that you could add up infinitely many numbers and still get a perfectly finite answer? Most people think that's impossible. The common assumption is that adding infinitely many positive numbers must give you infinity. After all, you're adding forever, so the sum should grow without bound, right? But here's the amazing truth. This particular infinite sum actually equals exactly 2. Not approximately 2, but exactly 2. This is the magic of infinite geometric series. Welcome to our complete guide to infinite geometric series. An infinite geometric series is a sum where we add up infinitely many terms, and each term is found by multiplying the previous term by the same constant ratio. In this comprehensive video series, you'll master 3 crucial skills. First, you'll learn to identify when an infinite geometric series converges to a finite sum versus when it diverges to infinity. Second, you'll discover the elegant formula that lets you calculate these infinite sums instantly. And third, you'll see how these concepts apply to real-world problems in calculus, physics, and finance. By the end of this series, you'll have the confidence and skills to tackle any infinite geometric series problem. You'll understand not just how to solve them, but why the mathematics works the way it does. So let's begin this fascinating journey into the world of infinite sums. A geometric series is fundamentally different from other types of series you might have encountered. Understanding this difference is crucial for mastering infinite series. First, we need to distinguish between a geometric sequence and a geometric series. A geometric sequence is simply a list of numbers where each term is obtained by multiplying the previous term by a constant value. A geometric series, on the other hand, is the sum of all terms in a geometric sequence. Instead of just listing the terms, we add them together. Every geometric series can be written in this general form. Here, A represents the first term of the series, and it appears in every term of the series. The letter R represents the common ratio. This is the constant value that we multiply by to get from one term to the next. Notice how the exponent of R increases by 1 in each successive term. Now, let's look at a concrete example to identify the first term and common ratio. Consider the series, 2 plus 4 plus 8 plus 16, and so on. The first term A is clearly 2, since that's the very first number in our series. To find the common ratio R, we need to see what we multiply each term by to get the next term. Let's examine this step by step. From 2 to 4, we multiply by 2. From 4 to 8, we also multiply by 2. From 8 to 16, again we multiply by 2. This consistent multiplier is our common ratio. So our series 2 plus 4 plus 8 plus 16 and so on can be written in the general form as 2 plus 2 times 2 plus 2 times 2 squared plus 2 times 2 cubed, and so forth. The key insight is that this series continues forever. It's infinite. Each new term follows the same pattern. Multiply the previous term by the common ratio. This infinite nature is what makes geometric series so powerful and interesting to study. To summarize, a geometric series is the sum of terms in a geometric sequence, where each term is obtained by multiplying the previous term by a constant ratio. The general form is a plus AR squared plus AR cubed, and so on, where A is the first term and R is the common ratio. Now we come to the most crucial question in infinite geometric series. When does an infinite sum actually equal a finite number? The answer lies in understanding convergence and divergence. The key lies in the common ratio R. Whether our infinite geometric series converges to a finite sum or diverges to infinity depends entirely on the absolute value of this ratio. Here's the fundamental rule. If the absolute value of R is less than 1, the series converges and has a finite sum. If the absolute value of R is greater than or equal to 1, the series diverges. Let me show you visually why this makes sense. When the absolute value of R is less than 1, each term in our series gets progressively smaller and smaller. Watch what happens to the terms. Starting with A equals 1, each successive term is half the size of the previous one. The terms shrink rapidly towards 0. Notice how the terms are getting smaller and smaller, approaching 0. This shrinking behavior allows the infinite sum to settle on a finite value. Now contrast this with what happens when the absolute value of R is greater than or equal to 1. The terms either stay the same size or grow larger with each step. With r equals 2, each term doubles in size. Starting with a equals 1, we get 1, then 2, then 4, then 8, and so on. The terms grow without bound. The terms keep growing larger and larger, heading toward infinity. There's no way this infinite sum can equal a finite number. Here's the intuitive way to think about it. When r is a fraction between -1 and +1, you're repeatedly multiplying by something smaller than 1, which makes terms shrink towards 0. But when the absolute value of r is 1 or greater, you're multiplying by something that keeps terms the same size or makes them bigger, preventing the sum from settling on a finite value. Remember this critical condition. The absolute value of r must be less than 1 for convergence. This is the gateway that determines whether an infinite geometric series has a finite sum or not. Now that we understand when an infinite geometric series converges, we can derive the powerful formula that gives us the exact sum of any convergent series. The formula for the sum of an infinite geometric series is S equals A divided by 1 minus R. This elegant formula connects three key components that completely determine the series. Let me break down each part of this formula. S represents the sum we're trying to find, the total value that all infinite terms add up to. The letter A represents the first term of our series. This is the starting value that begins our infinite sequence. Finally, R is the common ratio, the constant factor we multiply by to get from one term to the next. This ratio determines whether our series converges or diverges. This formula only works under one critical condition. The absolute value of R must be less than 1. This is the convergence condition we discussed earlier. But why does this formula work? To understand this, we need to see how it comes from the behavior of finite geometric series as they approach infinity. For a finite geometric series with n terms, the sum is given by this formula. Notice it has an extra factor involving r to the power n. Here's the key insight. When we take the limit as n approaches infinity, and the absolute value of r is less than 1, then r to the power n approaches 0. This means our finite formula transforms. The r to the power n term disappears, leaving us with a times 1 minus 0 divided by 1 minus r. Simplifying 1 minus 0 gives us 1, so our formula becomes a times 1 divided by 1 minus r, which simplifies to our final formula. This beautiful result shows us that we can find the exact sum of infinitely many terms using just two pieces of information, the first term and the common ratio. Remember, this formula is only valid when the absolute value of the common ratio is less than 1. This condition ensures that our infinite series actually converges to a finite sum. Now let's work through our first example to see how the formula works in practice. We'll find the sum of a simple infinite geometric series. We want to find the sum of the infinite geometric series, 1 plus 1/2 plus 1/4 plus 1/8, and so on. Step 1. We need to identify the first term a and the common ratio r from our series. The first term a is simply the first number in our series, which is 1. To find the common ratio r, we divide any term by the previous term. 1/2 divided by 1 equals 1/2. 1/4 divided by 1/2 also equals 1/2. Now that we've identified our values, let's check if this series converges. Step 2. We must verify that the absolute value of r is less than 1 for the series to converge. The absolute value of 1/2 equals 1/2, which is indeed less than 1. Therefore, our series converges and has a finite sum. Since the series converges, we can now apply our formula to find the exact sum. Step 3. We apply the formula S equals A divided by 1 minus R. We substitute our values, A equals 1 and R equals 1/2 into the formula. Now let's calculate this step by step. First, we calculate the denominator. 1 minus 1/2 equals 2/2 minus 1/2, which equals 1/2. Now we divide 1 by 1/2. Dividing by a fraction is the same as multiplying by its reciprocal. So 1 divided by 1/2 equals 1 times 2 over 1, which equals 2. Therefore, the sum of our infinite geometric series is 2. This means that if we could somehow add up all the terms in the series 1 plus 1/2 plus 1/4 plus 1/8 and so on forever, the total would equal exactly 2. This example beautifully demonstrates how an infinite number of terms can add up to a finite value when the terms get smaller and smaller in just the right way. Now we'll explore a fascinating application of infinite geometric series, converting repeating decimals into fractions. This is one of the most practical uses of geometric series that you'll encounter in mathematics. Consider the repeating decimal 0.3333, continuing forever. Our goal is to express this as a fraction using infinite geometric series. First, we need to break down this repeating decimal into individual terms. 0.3333 can be written as 0.3 plus 0.03 plus 0.003, and so on. Notice the pattern here. Each term is exactly 1/10 of the previous term. This constant ratio is what makes this an infinite geometric series. Step 2, we identify the components of our geometric series. Comparing our series to the general form a plus ar squared and so on, we can see that our first term a equals 0.3. The common ratio r equals 0.1, since each term is multiplied by 0.1 to get the next term. Step 3, we must verify that our series converges. For an infinite geometric series to have a finite sum, the absolute value of r must be less than 1. Since the absolute value of 0.1 equals 0.1, which is indeed less than 1, our series converges and has a finite sum. Step 4. Now we apply the formula for the sum of an infinite geometric series. The sum s equals a divided by 1 minus r. Substituting our values a equals 0.3 and r equals 0.1, we get s equals 0.3 divided by 1 minus 0.1. Simplifying the denominator, 1 minus 0.1 equals 0.9. Step 5. To get our final answer, we convert the decimals to fractions. 0.3 equals 3/10 and 0.9 equals 9/10. When dividing fractions, we multiply by the reciprocal. So 3/10 divided by 9/10 becomes 3/10 times 10/9. Multiplying 3 times 10 equals 30, and 10 times 9 equals 90. So we have 30 over 90. Reducing 30 over 90 to lowest terms by dividing both numerator and denominator by 30, we get our final answer, 1/3. Therefore, the repeating decimal 0.3333 equals exactly 1/3. This demonstrates the power of infinite geometric series in converting repeating decimals to exact fractional form. Now we'll examine our third example, which demonstrates what happens when a geometric series diverges. This is a crucial concept because it shows us when we cannot apply our sum formula. Consider this geometric series, 1 plus 2 plus 4 plus 8 plus 16 plus 32, and so on. Notice how each term is exactly double the previous term. First, let's identify our key values. The first term a equals 1, and the common ratio r equals 2, since each term is multiplied by 2 to get the next term. Remember, for an infinite geometric series to converge, we need the absolute value of r to be less than 1. This is our crucial convergence condition. Now let's check our condition. The absolute value of 2 equals 2, which is greater than or equal to 1. This violates our convergence condition. Since our condition is violated, this series diverges. Let me show you visually what this means by demonstrating how rapidly the terms grow. Here's a visual representation of the first 6 terms of our series. Notice how each bar is exactly twice the height of the previous one. Each term is obtained by multiplying the previous term by 2. This doubling pattern continues indefinitely. As we continue this pattern, the terms grow without bound. Let me show you what happens to the partial sums. Now let's look at the partial sums. The first partial sum is just 1. The second partial sum is 1 plus 2, which equals 3. The third partial sum is 7. The fourth is 15. The fifth is 31. And the sixth is 63. Notice the pattern, 1, 3, 7, 15, 31, 63. These partial sums are growing rapidly and will continue to grow without bound, approaching infinity. This is what we mean by divergence. Since the common ratio has absolute value greater than or equal to 1, we cannot use our sum formula. The key takeaway is that this series diverges because the absolute value of r equals 2, which is greater than or equal to 1. We must not apply the sum formula in this case. The sum of this infinite series is undefined and approaches infinity. This is a fundamental concept in understanding when infinite geometric series have finite sums and when they do not. Now that we've explored infinite geometric series through examples, it's time to recap what we've learned and see how these mathematical concepts apply to the real world around us. First, we learned that an infinite geometric series is the sum of an infinite geometric sequence. It has the form a plus ar squared plus ar cubed, and so on, continuing forever. Second, we discovered the crucial convergence condition. An infinite geometric series converges to a finite sum only when the absolute value of the common ratio r is less than 1. Third, we learned the powerful formula for calculating the sum. When the convergence condition is met, the sum equals a divided by 1 minus r. Now, you might be wondering where infinite geometric series actually appear in the real world. The answer is everywhere. These mathematical concepts help us model and understand many natural phenomena and technological processes. First, infinite geometric series help model population growth. When a population grows by a constant percentage each year, we can use geometric series to predict future population sizes and understand long-term trends. Second, radioactive decay follows geometric patterns. As radioactive materials break down at constant rates, geometric series help scientists calculate half-lives and predict how much material will remain after any given time period. Third, in computing and technology, geometric series appear in algorithm analysis, computer graphics, and signal processing. They help optimize code performance and create smooth visual effects. Fourth, in economics and finance, these series help calculate compound interest, loan payments, and investment returns. They're essential tools for financial planning and economic modeling. Before we finish, here's the most important reminder. Always check that the absolute value of r is less than 1 before applying the sum formula. This condition determines whether the series converges to a finite value. Congratulations! You now have all the tools you need to confidently tackle infinite geometric series. You can identify them, check convergence conditions, apply the sum formula, and even solve real-world problems. If this video helped you understand infinite geometric series, please give it a thumbs up. Leave a comment if you have questions or want to see specific topics covered. And don't forget to subscribe and hit the notification bell for more math tutorials that will help you succeed in your studies.